Hello there, welcome to John Stewart's Calculus Early Transcendentals 9th edition. We're dealing with problem number 35. And so the instructions say to find dy over dx and dy over dt. That means we are going to have to take two derivatives, not just one. Alright, so your first step here is basically you want to identify what you're doing. So thankfully our basic polynomial derivative rule is just x of n. When you take the derivative, the n comes in front and you subtract 1 from the n. And luckily our problem looks exactly like that, so we can just hop right into it. But a quick thing to notice is they're asking for two different types of derivatives, so what's the difference between dy over dx and dy over dt? Basically, you can think of the first expression as being how fast is y changing with respect to t, or with respect to x, and the second one is how fast is y changing with respect to t. It's basically how fast the upstairs is changing with respect to downstairs. So if x moved on a graph 1 unit to the right, how much would y change? Would it go up by 2? Would it go down by 2? That kind of idea. So what would this mean? If you had d height over d years old, what would you expect? How does height change with respect to your years old? Well, it would basically be whether you're growing taller or whether you're shrinking and how your height is changing relative to how old you are. So as an example, if you were a baby, you're probably growing pretty fast. If you're a teenager going through puberty, you're probably growing pretty fast. If you're in your 30s, yeah, your height's probably pretty much the same, probably not changing. So your height's probably equal, or your change would be equal to 0. And by comparison, when you get really old, it might even go to negative. So how does this help us with this problem? Well, on the next slide, we'll deal with that. Okay, so the first step is I like to think of each term as being its own little derivative problem. So basically I think of taking dy dx as taking the derivative with respect to x of that first term, and then the derivative with respect to x of the second term. Step 2, we want to take our constants out front, and in this case, notice I put the x on the bottom in bold. You can think of the x as being like a big wall, where Gandalf is basically saying x will not pass. So as long as the term doesn't have x in it, you can pretty much move it out front. And now let's apply our basic polynomial derivative rule. And so here we're basically applying the derivative to the x because it's still inside our derivative. So we are taking the 2, we're putting it down out in front, and we're subtracting 1 from it. And with the second term, you have to remember there's kind of like a hidden x to the 1. So if you subtract 1 from 1, you're just going to get x to the 0. And of course x to the 0 is the same as being 1. And so of course 1 times 1 is just going to get you back that t cubed. So all that I've done at the bottom is I've just kind of cleaned it up a little bit, and that is basically the solution to the first part. But the question is, what would change if you had dy over dt? And we'll deal with that on the next slide. Okay, so the first part of the problem, we're going to do the exact same approach. We're going to treat each term like its own little mini derivative. We'll take the derivative of the first term, then the derivative of the second term. I've highlighted in bold here that the t, because the t now is kind of like the wall where Gandalf is saying t shall not pass this time. So anything that doesn't have a t can come out in front. So those x squareds and the x, they can just jump out in front. Now we're going to apply our basic polynomial derivative rule. And here, basically what we're doing is we're taking that t, which you can think of really as being t to the power 1, and we're subtracting 1 from it, and we're moving the old exponent in front. Of course, multiplying by 1 doesn't really do anything, so you don't really have to write it. I just wrote it just to be explicit. With respect to the second term, you have that t cubed, so the 3 from the cubed comes in front, and we subtract 1 from that 3. So just basically going through and doing the basic math, 1 minus 1 is of course 0, so you get t to the 0. 3 minus 1 is 2, so you get t squared. And from there, just remember that t to the power 0 is not 0, it's 1. That's a common mistake that people make. So here you just have x squared is 1 times 1, or x squared times 1 times 1. Timesing something by 1 doesn't change its value, so you just have x squared plus, and I just cleaned up the second term there. And so that's the solution to dy over dt. So the important thing to learn from this problem is you're just trying to determine what's the difference between when you're doing dy over dx or dy over dt, and it's basically what is considered to be a constant. If it's over dt, you're taking the derivative with respect to t, so all the x's can come out in front. And yeah, that's pretty much it. If you're looking for a solution to another problem, let me know, and I'll try to do my best to give you sort of a step-by-step breakdown how to solve it, and point out what the question is trying to teach you. If there's a specific problem, just leave the question and maybe textbook number below, and I'll see if we can get to it. Have a good day.